All right. So I didn't post another set of lecture slides. We're going to work off of last week. So week 11, the last couple problems are at the end of the slides. We'll kind of work on some of those. Probably starting on Wednesday and Friday, we'll start going over some of the problems from the practice exams. So this will be a lot of hypothesis testing. Probably I'll go back and do some review of some older stuff on Wednesday. Friday, we'll probably start to do, kind of bleed into confidence intervals and hypothesis testing again. And if you have any specific problems, as you start working through those practice exams, we can always start with those problems, right? That's the whole point of doing the review, is to be beneficial for you. So if I'm going over problems that you already know how to do, that's kind of, that's pointless. So if you show up in person or on Zoom and you have specific problems you want to work through, I'll start going through those first, okay? All right, so we'll start on this question 2, where we have kind of here, I don't have anywhere identifying the null and alternative, so we're just going to be mainly kind of working through the process of the hypothesis testing. I'll kind of state what this would mean. So here, if we were looking at a problem, this null and alternative hypothesis would correspond to something like, suppose we want to test for whether or not the true proportion of handgun owners or something in the US is less than 45% or less than 0.45. We would assume the opposite is true, which is that it's greater than or equal to that 0.45. We then think about what type of tailed test do we have here? Well, we always look at the alternative hypothesis. So we've got a less than sign. So we're going to be thinking about a left-tailed, or kind of this less than test, right? We're looking at the left side of that distribution. So 3 and 4 make this a little bit easier, and there are definitely some numbers we could play around with. But let's start with kind of number 1, right? So if I told you, that the number of people that own guns were 36 in this survey out of 109 people surveyed, right? Well, what's my sample proportion there, right? So anytime I'm not given directly, right? I'm not given P bar or P hat, whatever we want to call that sample proportion. I can figure out what that is if I know the number of successes out of the number of trials, right? Or the number of whatever I'm looking for out of the total number of observations, right? So there, if I've got X is 36, and I think it was 109. I might be a little bit off on that. We'll correct that number if it is. If I want to find my sample proportion, I simply take, it was 106, sorry, 106. It was 36 out of 109, right? So I actually brought my calculator with me today, so I can work along kind of these with you. We get about 0.33 here. I guess this is the point where I should make sure that that was 109. I wasn't thinking about that incorrect. Yeah, 109, right? So we've got our sample proportion now of 0.33, right? And what we've assumed, let me use a different color because this isn't showing up very good, so hopefully the blue shows up a little bit better here. There you go. We know our sample proportions will be distributed normally around whatever that assumed true proportion is, right? Or that's what we're assuming that this is going to be the proportion. So assumed true proportion was what, 0.45 here? We're thinking about, we have a left tail test, so really only evidence on the left side of this distribution will be something that goes against the null. Because the null was that we assumed it was 45% or greater, or 0.45 or greater. So we find 0.33 as our sample proportion. We could use the critical value or the p-value approach. So the first one we'll work through, let's do the p-value approach first, and then we'll talk about the critical value approach. So I have a normal distribution, but that doesn't help me if I want to use the tables, right? So I want to turn this into a standard normal distribution by turning that sample proportion I found into a test statistic, or because it's coming from that standard normal distribution, into a z-statistic. Right? So how do I do that? Well, one of the equation that we've talked about last week was, if I have kind of this sample proportion, I'll take the value I found from my sample proportion, subtract the assumed true proportion, which came from my null and alternative hypothesis. Let me make sure I have this showed up so I can. All right. I then divide by, remember, these test statistics always take the format of, take the statistic you're interested in, the sample statistic, subtract the assumed true value for that statistic, and then divide by the standard deviation of that statistic. Now we have an equation for that, right? The standard deviation of our sample proportions. Well, typically we would use the population proportion here, but all we have is the assumed true population proportion, right? We then divide by our sample size, and this would give us our test statistic, right? So we plug in 0.33 here, we plug in 0.45, 0.45, 0.45, our sample size, 109, right? So we kind of think about 0.33, 0.45 will go here, here, and here, and then our sample size was 109. Okay? So we're just plugging our values in to that test statistic equation. If we go ahead and do that math, should get, I think, let's make sure I have everything, negative 2.52 approximately. So negative 2.52. And that looks like a reasonable answer, right? I'm 2.5. Remember, these are still Z values, these Z statistics. So what this is really saying is the sample evidence I found was 2.5 standard deviations below that assumed true value. And that kind of makes sense, right? I mean, we're definitely should be getting a negative test statistic because we're below the assumed true value. We're pretty far away, right? When we're dealing with proportions, I mean, the entire range you could ever see is between 0 and 1. So being 0.12 away is pretty far. So 2.5 standard deviations seems reasonable. So, you know, just to kind of check around, if we would have seen something like, I don't know, positive 0.3, well, that would mean that we were barely above that assumed true value. Well, clearly, if we draw this out, we can see that that's not the case. So we've got our test statistic, or our Z statistic now. So we'll put that here on the graph. We're dealing with a left-tailed test. So our p-value is going to be the probability that we saw the sample evidence we did that was as far away from the assumed true value or anything even further. So in the left-tailed case, left-tailed test or less than test, that's anything to the left, right? If we had a right-tailed test, it'd be anything to the right of our test statistic. So if I have a standard normal distribution, I can look up this value, right, on my table. The table tells me the area to the left of that value, and for a left-tailed test, I'm done, right? Left-tailed tests are kind of nice and easy there. So if I go ahead and do that, what do I get here? Negative 2.52, 0.0059. Right here, negative 2.52. The area to the left is 0.0059. Okay. So I put that area up. Okay. And this is kind of represents my p-value. So what's my rejection decision? Well, I didn't specify any alphas here, but we could test against several different alpha values. Right? So I'm going to erase this. Hopefully, everyone kind of had that jotted down up to this point. But we only reject if our p-value is less than alpha, right? Going into the next exam, I mean, I would write this down, you know, burn this into my memory, make sure I have this in front of me because it's always the same rejection decision, right? So is my p-value of 0.0059. I think an easy way to do this, we usually test against 3 alpha values, right? We usually have the 1, 5, and 10% significance levels, which correspond to alphas of 0.1, 0.05, and 0.01. Okay. So is 0.0059 less than 0.1? It sure is. So we reject at the 10% significance level. Is it less than 0.05? Well, notice this is 0.005, so yes. So we can reject. Is it less than 0.01? Sure enough, it is, so we can reject there as well. So this was an example where based off the sample evidence we found, we could reject the assumed true value at every level of significance, right? You know, and that makes sense. We found a value that's pretty inconsistent with what we assume to be true. So if it's pretty inconsistent with what we assume to be true, or it has a low probability that we saw that value, if in fact 0.45 was the true population proportion, well then it makes sense we can reject that assumption, right? Now, one thing that I want to point out here is if we had made the mistake of treating this like a two-tailed test, right? And we multiplied the area of the tail by 2, well, if we do that, this actually gets larger than 0.01, we would have made the wrong rejection decision there. So we need to be careful when we're finding that p-value. The only time we multiply that area of the tail by 2 is if we have a two-tailed test, okay? Any questions on that one up to this point? Okay with that? You don't have to look around at as many faces today to figure that out. So that's how we would do this if we had the p-value approach. We can do the same thing, but let's think about how we would tackle the critical value approach. So with the critical value approach, what we want to start out doing is say, let's find the critical value that gives us alpha in this left tail, right? So let's say our first alpha is 0.1. Well, if the area in the tail I want is 0.1, and I want to find the z-value, remember, these critical values are still coming from that standard normal distribution, so I kind of want this cutoff value that says, look, I mean, this isn't what it's going to be, but let's assume that we find that it's 1.5. What we're saying is if I get a test statistic, negative 1.5, if I get a test statistic that shows that the sample evidence I found is any more than 1.5 standard deviations away from that assumed true value, then I'm okay rejecting it, right? Because this would be my rejection region. Now, I just made this number up to be able to say a number there. We want to actually find what that value is, right? What that cutoff value is. So we want an area of 0.1 in that lower left tail. Well, that's what the standard normal table is set up as. Well, I no longer have the z-value. That's what I want to find. I know the area I want in the tail, so I'm going to look that number up in the middle of the table here. So 0.1. Oh, where's the closest? Looks like in between these two. So negative 1.28 and negative 1.29. We'll kind of take the higher of the two or round that up to the highest one. So negative 1.29. Our critical value here, negative 1.29. If we're only going to be testing against this one alpha, I would then say, okay, what does my sample evidence turn into a test statistic-wise? I'll plot that. It was what, negative 2.52, clearly in the rejection region, right, at the 10% level. So we would say with 10% significance, we can reject the null hypothesis here. And we would do the same process if we were looking up alpha, the next two alphas of 0.05 and 0.01. Now, one easy way we could do this, and we can look it up in the standard normal table. The process is a little cumbersome to look up all three. If we remember that this student t table, the last row essentially is telling us the standard normal distribution values that we would have found, but out to the third decimal, so even more precise. So notice, if I wanted 0.1 in that tail, right, the value from the standard normal distribution that would give that to me is 1.282. Now, the way the t-table is set up, it's always looking at the right side of the distribution. So if I have a left-tail test, I have to remember, well, it would be this value, but negative, right? And so instead of having to round a negative 1.29, I could actually be a little more precise if I use that last row of the t-table, right? And either way is fine. I'm never going to give you an example where, the test statistic is like in between where you were rounding. But we could be a little bit more precise there. Another reason why it's nice to use that student t-table, that last row, to find the standard normal values is because notice, well now, if I want to test against several alphas, so let's say they're 0.1, 0.05, and 0.01, I can go down here and say, well, those critical values would be 1.282, 1.645, and 2.326. I've got a left-tailed test, so it would be all those same values, but negative. So I could then say, okay, probably have to give myself a little more room here. So I can write all these out. So if I wanted to put all three of those critical values, so negative 1.282, negative 1.645, negative 2.326, right? Those are those different, this corresponded to the 1% significance level, 5%, and 10%, right? So those were the values that would give me those three different alpha values in the tail. My rejection regions are anything more extreme than those critical values or larger in absolute value for left-tailed test, anything to the left. I then plot my test statistic of negative 2.52, which we found earlier. That would be all the way out here. It's clearly in the rejection region at every single significance level, which is exactly what we found using the p-value approach. Right? Now, when it comes to like the exam, you're never going to have to, I might ask you to do several approaches on, the same example. In practice, right, if I'm just trying to make a rejection decision, I only need to use one, okay? But we should know how to use both. We kind of even talked about, maybe I like the p-value approach here, but once I have to use those student t-tables, it's harder to find a p-value using the table. I can only get like a range or bound it, and so it's easier to do critical values. So I want to know how to do both approaches. Okay? Anything else I want to say? Any other questions on this one before we keep going? All right, so I'm going to rewrite this up here. So we have it as something to reference here in just a second. So here was our test statistic equation, right? For proportions. Okay? So let's assume that I had instead, where are we? Taken a sample of 283. What does that end up being? Yeah, so let's say, for the sake of what I'm going to do, actually, I think maybe let's change this to 95, I think, because I want to prove a point here. Let's do 94, 93. Okay, let's assume instead I had 94 here, right? If you now try to find that sample proportion, 94 out of 283, you get about 0.33. So probably could have chosen better numbers here to kind of show this point so that you would get the exact same sample proportion. I think they're off to like the third or fourth decimal. But if we look at the second decimal, this sample proportion, 94 out of 283, would still be a sample proportion of 0.33, right? Which is what we found from kind of problem one here with a smaller sample size, okay? So I've found the same sample proportion, but with a higher sample size. Everything else in this problem has remained the same, right? I still have the same hypothesis test. I've got my same sample proportion. So when I think about what changes in this equation, I'm going to have the same sample proportion, same assumed true proportion. When I draw this out, it's going to look exactly the same. The only thing that's going to change is my sample size is now much larger. Now, we talked about this a little bit last class, but I really want to kind of hammer this home because I could ask you questions that relate to this on the exam, right? If my sample size goes up, right, what's going to happen to this denominator? Or remember, this denominator is the standard deviation of my sample proportions. Well, as we take higher and higher sample sizes, this standard deviation, or this kind of think about as the variance, will go down. Yeah. As this goes down, I get a much more peaked distribution. Well, now, seeing that same sample evidence, the probability of seeing that or anything further away from the assumed true value is going to be much lower, right? Now, I can go ahead and I can calculate my test statistic, if the denominator is smaller, what happens to my test statistic? Gets higher? Well, think about it. If my test statistic is getting higher, what's happening to the area to the left of it? It's getting smaller, right? Which is what we have here visually. So when this happens, when I have a higher test statistic, and when I say higher here, higher in absolute value, right? We had a negative test statistic. It's going to become a larger negative value, right? So my p-value is going to go down because my test statistic, think about it this way. We found the same sample evidence. So let's say it's still 0.12 away, but now we have a much smaller standard deviation. So being 0.12 away is going to be many more standard deviations away, right? If my standard deviation before was, say, 0.06, I would have been 2 standard deviations below. If it's now 0.03, now I'm 4 standard deviations below, right? So as my p-value goes down, when we think about that rejection decision, is if the p-value is less than alpha, if this gets smaller, it's going to be more likely that I'm less than alpha. So with a smaller p-value, you can say that we're more likely to reject, right? So kind of these red lines, if you wanted to write them out line by line as a step. Number 1, a higher sample size will lead to 0.2, a smaller standard deviation. That will lead to a higher test statistic, which leads to a lower p-value and makes me more likely to reject. Right? Now I could work through all this again, resolve it, and prove this to myself, right? Plug the numbers in. I'll end up with a higher test statistic. Once I have that test statistic, look it up in the standard normal table. I'll find a smaller area to the left, which would mean a smaller p-value. I'd then be more likely to reject at different alphas. Right? So I can prove this to myself by reworking it. But just kind of that thought process, I think, is important. I really want to kind of hammer that home, okay? Any questions on anything I said there? Okay with that? Okay. All right. So I'm going to skip 3 and 4. If you wanted to, just kind of, there's some more problems you could work through. Same kind of thing we could prove here. If you got the same sample proportion, we take a higher sample size, same sort of things would apply. Okay? There's another proportion example, but I want to make, or no, this is a mean. Sample variances, which one do I want to do here? Which one do I like more? Let's do this one right here. But I'm going to change some things here just so we can prove something. I want to do the same sample mean here. Let's do a slightly higher. Let's do 9.6 here. Okay. So we'll kind of work off the numbers from 1 and 2 here that I just changed them a little bit because I just made a point in the previous one, so I want to make the opposite point now. Okay, so I have kind of this hypothesis, which we maybe can think about as, we could go back even to that example way back when it was the economists wanted to test for is the mean retirement age different than 73, something like that. Right? So we want to find, is it different than 73? So we assume the opposite is true, which is that it's equal to 73. Right? So I ask here for the range of the p-value. We're just going to work through the entire thing, every single step of that p-value process. So I have a sample mean of 70. I have a sample standard deviation of 6.9, and I have a sample size of 35. Right? I don't have a population variance, so I now know, unlike the previous problem, I can't use the standard normal distribution. I'm going to have to use that student t distribution. Right? So these are our kind of values that were given. Let's think about how we could work through this example. Black markers really sticks up here. Oh, I didn't switch it. That would be helpful. All right. So we're looking at distributions of sample means. We know that if what we assume to be true was in fact true, they should be centered around that assumed true value of 73. Okay? We found a sample mean of 70, but for a two-tailed test, it would have been equally as likely that we had found something above that assumed true mean, but on the right-hand side. Right? So we can turn our value into a test statistic, find the p-value, but we have to remember that's only half of our p-value. So once we find that, we have to multiply it by 2. So it's going to look visually kind of similar to what we did before. It's just now, instead of turning that sample mean, before we turn the sample portion into a z-value, if we only have the sample standard deviation or sample variance, we turn the sample mean into a t statistic or a test statistic that comes from a student t distribution. Right? Same sort of idea. This area to the left of it, we could then look up, which would be half our p-value. We've got two-tailed tests, so we need to multiply it by 2. So how do we turn this into a test statistic? Well, the equation that we had for that was your sample mean minus your assumed true mean. We're still going to be dividing by a standard deviation of our sample means. It's just now we notate it a little bit differently because we're not using the population variance. We're using, my finger's not erasing this as easy. That's good today. We're only using the sample variance. Okay? So I plug my sample mean in, plug that assumed true population mean in. Now here I got to be careful. I was given the sample standard deviation of 6.9. When I plug that into my equation, that is just S. So I'll have to square that value, right, if I'm entering that into my calculator. And then our sample size was 35 here. So let me work along. So we get what? -3 on top divided by the square root of 6.9 squared divided by 35. So -2.57. Okay?
How do you change S to 9.6?
I think that was in problem 2.
Problem 2.
Did I mess up? Hold on. I might have. No, yeah. We're working off problem 1 numbers for now, but we'll get there. In fact, if you calculated that, if you have it in your calculator, write it down. It'd be helpful for me to know so I don't have to enter it into mine. So -2.57 is our test statistic right here. Once again, kind of makes sense. We found evidence below what we assumed to be true. We're not very far away, but we had a relatively low variance here, so maybe it is quite a few standard deviations. So now I go to my student t tables to find the area to the left of that value. Now we have kind of a pain with that student t table, which is that it always is giving us the values that are, oh, where's that picture? There it is. To the right, right? We're dealing with the right side. Well, here we're dealing with the left side of the distribution. It basically be everything that we have here, but the numbers in the middle here would just be negative, right? Because it's a symmetric distribution. So we had -2.57 at what degrees of freedom? Well, if our sample size was 35, degrees of freedom is just n-1. So we'll have degrees of freedom of 34. So we go to that table. 34 is our degrees of freedom. All right. We try to find 2.57. We go over here. Well, I don't have exactly 2.57, but it would be somewhere in between these two values, right? So if the area kind of to the left of -2.44 is 0.01, and the area to the left of -2.72 is 0.005, I know the area to the left of -2.57 is somewhere in between there, right? So I see what test, I look up what t values my test statistic is in between, make sure I'm on the right line. So it's in between these two. So I know the p-value is somewhere in between 0.005 and 0.01. And I actually technically said that incorrect. I don't know the p-values in between those two areas, or in between those two values. I know that the area in this left tail is in between those two values. Right? So here, I know that half of my p-value, or that area in the tail, is in between 0.01 and 0.005. Right? But that only represented that area and that tail was only half my p-value. So I know that over here, this area is also in between 0.005 and 0.01. So the total area in those tails has to be somewhere in between. And I can think about this a couple different ways. I could simply add up these lower bounds and upper bounds, or I could just say, well, look, I'm going to treat this like any other example. If I know that one area is in between this, I'll multiply these by 2. So if I do that, I know my p-value would be somewhere in between 0.01 and 0.02, right? All I'm doing there, multiplying those by 2, just like I would in any other problem, any left or right tail test problem. Or not left or right tail test, sorry. If I was doing this with like a standard normal distribution problem. So now I know my p-value is somewhere in that range. I can now make my rejection decision. Okay? So we'll set this up the same way we did before. But now my p-value is somewhere in between. Nope, I multiplied these by 2, so it was 0.01 and 0.02, right? So if my p-value is somewhere in this range, is it less than 0.01? Well, this is telling me, in fact, it's greater than 0.01, right? So if my p-value is in this range, at an alpha of 0.01, I would actually fail to reject. What about 0.05? Well, I know my p-value has to be less than 0.02, so it's definitely going to be less than 0.05, so I can reject at that level. If I can reject with 95% confidence, am I going to be able to reject with 90% confidence? Yes, because if my p-value is less than 0.02, it has to be less than 0.1, so it doesn't look like an R there, hold on. So I reject there as well, right? So here we have an example. Notice, we're dealing with that student t-distribution. It's a little bit more spread out. So even though I found a similar test statistic, my p-value was a little bit larger than in the previous problem. So now, even with its, I think actually this is a larger test statistic, right? Didn't we say it was negative 2.52 in the previous problem? Well, here it's a little bit bigger, right? But we end up not being able to make kind of the same rejection, right? We only reject at the 5 and 10% significance levels, not the 1%. Right? Any questions on anything there? Let's see the chat here. Okay. Now we could also do the critical value approach. Where are we at in time? Oh, we're good. So I think, if this bounding the p-value is kind of confusing, I think the p-value approach here, when we're dealing with that student t-distribution, might be the way to go. All right. So we got this student t-distribution. Let's think about for the very first one, what do I really want with my critical value? Well, here, I have a two-tailed test, so I'm actually going to have two critical values, such that alpha total is in the tail, but because I have two sides, it's the critical values that give me alpha over 2 in each tail. Okay? I have my same, I erased it, my same degrees of freedom, which was 34. So what I'll do is, I'll go to that degrees of freedom. What's the area that I want in my tail? Well, if my alpha was 0.1, when I divide that by 2, so let's say we start out with this alpha of 0.1 first. When I divide that by 2, I would have 0.05 in each tail. So I'll look up 0.05 and find the t-value. That would give me 0.05 in the tail at degrees of freedom 34, 1.691. Excuse me, so 1.691, but remember, if we drew this out as a two-tailed test, it's kind of easy to remind ourselves, we have two critical values, so 1.691 and positive 1.691. Here's our rejection regions, kind of drawing those arrows into the tail. If I then plot my test statistic of negative 2.57, I can clearly see that's in my rejection region, right, at the 10% significance level. I would then go through this process again for the alpha is equal to 0.05 and alpha is equal to 0.01, or I could just draw them all up there at one time, right? Kind of like we did in the previous one. So I'm just giving myself a little more room. I'll put that test statistic on there again. But now I want to find the critical values that would give me an alpha of 0.05 in the tail. All right, so now I divide that by 2, 0.025. I go to my student t-table, degrees of freedom 34. Area I want in the tail, 0.025. 2.032 would be the critical value. But remember, it's a two-tailed test, so it's that value, but also negative. So negative 3 something, and positive 2 point, that doesn't sound right. Is that right? 2.03. I was going to say, that seems a little high. So 2.03 and negative 2.03. Rejection region. Then I go to the next level, alpha of 0.01. Divide that by 2, 0.005. Go to my table, 0.005, degrees of freedom 34, 2.728. Okay? Now I could have just looked those all up at the same time. If I said, okay, if I have an alpha of 0.1, 0.05, and 0.01, if I divide all those by 2, I'd have 0.05, 0.025, and 0.005, and just grab those numbers all at once. I don't have to kind of continuously do this one at a time. So 2.728. So I'm going to extend this a little bit. So negative 2.728, positive 2.728, right? Rejection regions would be anything to the left of it. Now when I plot my test statistic was negative 2.57, you can kind of see what's in the rejection region here, but not for this last critical value. Remember, this was the critical value of 1%, 5, and 10. So just like the p-value approach earlier, we can reject at the 10 and 5% levels, but we fail to reject at the 1% significance level. So you can kind of see here, if we do the critical value approach, we don't have to worry about like bounding anything. We can find the exact values and plot our test statistic. So I think with the student t-tables, that approach is a little bit easier. So if I left you, question open-ended, and asked you for a rejection decision and then show your steps to proving it along the way, you only had to choose one. I would probably choose the critical value approach if I'm dealing with a student t-table. Now, if you're doing it, and if you're working Excel, I mean, then it, the point is moot, right? We kind of showed how you can use that t.dist function, get the exact p-value. We don't have to worry about kind of dealing with those tables. Any questions on that? Okay with this? Good? So, the setups look similar regardless of what type of distribution we're looking at. And so I want to walk through kind of the thought process here. So let's say I have this example 2. Everything's the same, but I have a higher standard deviation, sample standard deviation. Well, what's going to happen? Once again, I'll rewrite the formula we're using. It's not a z-value, it's a t-value. So we have this. So the sample variance goes up. What happens to the standard deviation of our sample means? Well, it gets higher, which means we have kind of this flatter distribution, which means seeing the same sample evidence is now more likely, right? Which means a higher p-value. But we can prove that because if my denominator is larger here, my test statistic gets smaller. If my test statistic gets smaller, well, now the area to the left of it, or even if it's only half my p-value, once I multiply it by 2, my p-value will now also, my p-value will get much larger, right? If my p-value gets larger, right, I'm less likely to reject because now if my p-value, moves from being in between 0.01 and 0.02, it increases all the way up to say 0.2. Well, now it's not going to be less than any of my alphas. So now I'm less likely to reject than I was before. So changes in kind of that sample variance, changes in the sample sizes, kind of thinking about how those would impact our test statistic, or why I kind of kept those numbers the same there, right? And you could work through it all. You plug all those numbers into your test statistic equation, bound the p-value again, and kind of prove to yourself that, in fact, this all would be true, right? But ahead of time, you should automatically know that, right? If I found the same sample mean, but a higher variance, right? I'm going to end up with it was more likely for me to see that, or a higher p-value, which means I'm less likely to kind of reject the assumed true value. Any questions there? Once again, all this kind of what I have here in red, right? That was kind of what you could write down in steps of how that initial change would have kind of led to these resulting decisions. I guess here I kind of went counterclockwise. Okay? Now, one thing I want to kind of point out here as well, without reworking a problem. So my sample mean I found was 70. Let's assume that we go back to problem 1, and I had that lower standard deviation of 6.9. So if everything else stayed the same, so I found the same sample standard deviation, I have the same sample size, but instead of seeing that sample mean of 70, let's say I saw a sample mean of 76. Should be able to tell me right away what the rejection decision is. So if we have those same numbers that we had from the first problem, before we changed kind of this standard deviation, but instead of seeing a sample mean of 70, I saw 76. For a two-tailed test, what's going to happen? Well, remember, when we calculate this test statistic, it's telling us the number of standard deviations away from the assumed true mean that we are. Well, I was 3 kind of units away from the mean before, which translated to about 2.5 standard deviations below. Well, if I find a sample mean that's 3 units above, what do I automatically know the test statistic will be? Not negative 2.57, but positive 2.57. When I find the area to the right, what would have been the same as the area to the left of negative 2.57? When I multiply by 2, I have the same p-value, which is going to lead me to the same rejection decisions, right? So if I see kind of the same sample mean to the left or the right for a two-tailed test, the only thing that's going to be different is I'll find the same test statistic, but for the value below it would be negative, for the value above it would be positive. Okay, and you know, because both of those are evidence equally as damning of that assumption that we made, right? It's just one happened to be on the other side. But we didn't care what side it was on. We just want to know, is it different than 73? So if we see 76 or 70, that's the same amount, or kind of you can think about it as like the same intensity of evidence that goes against that assumed true value. Okay? I'm losing my mask here. Okay, so you can almost think about it as that one that I just went through. Let's say we change this one. I kind of just described that scenario, right? Same sample standard deviation, same sample size. We just found a mean on the different side of that assumed true value, okay? And then I pulled this mean because I always thought this was a great mean, right? Can we reject that the alpha of 0.1? We did in all those problems, so I got 99 problems, but rejecting the null hypothesis ain't one. All right, this is a great stats mean. So I wanted to show, and this is a little, so before I kind of go to this, are there any other questions on kind of anything that we just did there? Anything up here? Okay with this? All right, so we'll do some more, maybe some more hypothesis testing, I guess, on Wednesday, but we'll definitely kind of start working through that practice exam. But I wanted to kind of take a step away from hypothesis testing for a second. I thought this was very relevant to the class and very relevant to the times. So I don't know. I don't really get too involved in the politics, but the stats of it fascinates me. So right now you have all these polls. People think they're wrong. People think they're right. You know, whatever. Like everyone's upset. So I was kind of looking at some of this data that's put out there. And you can like go to the different states. And so I think the one that I was looking at this morning was North Carolina was one of them. So you can click here, and it shows you a bunch of different polls that were done. Now, I don't know the specifics of all these polls, right? I could do some more research if I really wanted to. But kind of notice the way they're predicting these, right? And this one's very close, right? I mean, 0.2% difference. They're taking the most recent polls, right? And they're kind of averaging them, doing an average, right? Which, okay, yeah, that makes sense, right? If I don't want to just rely on one poll, like I'll take the average across several polls. That way, if any have a bias, I kind of can mitigate some of that bias that exists in that poll. Well, I looked at this and I was like, this really doesn't look right to me, because like this is way, like this one has like 2,000 people. This is our sample size. This one only has like a 450. So I shouldn't be, this one should mean a lot less to me than this, right? Higher sample sizes should allow us to kind of narrow down confidence intervals, more likely to reject. So I pulled this data somewhere. Here it is. So I think the first one I showed, yeah, this was North Carolina's, and Georgia's was the other one I did. So North Carolina. So notice these averages they showed that were 0.2 away. All they did there, I'll edit this to kind of show you. All they did there was take the average of these polls. What should they have been doing? Something we talked about before the first exam. If this poll has a much higher sample size and should be way more reliant, and this one has a much smaller sample size, why am I treating these the same? We would actually want to do a weighted mean, right? And weight this by however many people, weight this percent by however many people there were there. So I kind of set this up, multiplied the weights, added these up, divided by the sum of my weights here. And if I kind of format these as a percent so we can kind of compare these, you'll notice it's actually, in this state specifically, a much, quite a bit wider of a gap, right? We're over half a percentage point now, where before we were within 0.2, right? And you can go through and do this for every state, right? I did this for Georgia, same kind of thing. They're predicting it was 0.2, away, or 0.02. Here it's like not even 0.001 away. So Georgia right now is like insanely close, right? But if we just kind of look at the regular, don't do a weighted average, North Carolina and Georgia look like they're kind of just as tight of races, when in fact, Georgia here is kind of a much tighter race than, North Carolina, right? And you could kind of go through these points. I also thought it was kind of interesting if you look at this, which ones do you include? I'm sure some of these have somewhat political leanings, and so why did they not kind of go back to the 30th and just go back to the 31st here? They'll also show you that there's different results when you look at some of these that include third parties. So some of these polls don't kind of include third parties, some of them do, and so you can kind of look at differences across those. But when you actually just go to the original kind of site here, they're just showing you that average they calculated, which we just said they should have been doing a weighted average. So I don't really know how much to buy into any of this, right? I don't know how to kind of predict it just based off the numbers they're showing me here. So I don't know. I thought it was interesting that even like a major, I think it was maybe, it was CNN was kind of posting stuff from this 270 to win, which is even in a kind of intro to stats class, we can figure out what they're doing here is not going to be able to make the right prediction. Right? So anyways, hopefully after tomorrow, we won't have to do as many of these presidential examples. I'll kind of switch a little bit, but I think it's interesting. It's very relevant. Like I said, the stats kind of fascinate me. So we'll meet Wednesday, do a lot more kind of review from those practice exams, some more hypothesis stuff, hypothesis testing stuff as well. If you have any questions as you're kind of working through leading up to the exam, make sure you reach out, set up a Zoom meeting, kind of if you're trying to study or try to get some tips or trying to just help with the practice exams. I'm pretty open this week, so if you kind of schedule something with me, I'm sure we can find a time to meet. All right? All right, I will see you guys on Wednesday.